As enterprise AI deployments scale rapidly, organizations frequently fund a single centralized testing team, assuming that one unified group can secure the entire surface area. That assumption relies on a term that has lost all operational meaning. AI red teaming is completely overloaded. To cybersecurity professionals, red teaming means adversarial penetration testing of networks and infrastructure. To machine learning engineers, it means probing probabilistic model behavior and tweaking weights to see if a system can be manipulated. And to risk and compliance teams, the exact same phrase means auditing algorithms for bias and systemic demographic harm. These are three distinct disciplines with entirely different objectives. When you apply one label to all of them, enterprise governance is pulled in uncoordinated directions. When an AI deployment inevitably fails, ownership becomes heavily contested. Budget owners realize they don't actually know which specific testing capability they paid for. Linguistic ambiguity in enterprise architecture is a systemic vulnerability that actively creates shadow risks. A 2024 study by Carnegie Mellon University's Software Engineering Institute proved this out, finding that generative AI red teaming currently lacks standardized protocols across the industry. Microsoft's dedicated AI red team ran over 80 operations across more than 100 generative AI products. Even at that massive scale, Microsoft realized they had to separate their testing operations. A team looking for security flaws could not simultaneously measure the difficult-to-quantify dimensions of AI safety and bias. The solution is to retire red teaming as a monolith. In its place, we adopt a strict three-function taxonomy: adversarial AI testing, responsible AI evaluation, and AI security. This structure defines testing by its objective rather than its methodology. By separating the goals, we assign clear accountability to the correct engineering teams. Industry-level standards are still maturing. Enterprise AI programs require proactive, internal precision right now to function safely. The first pillar is adversarial AI testing. This discipline asks one core question: what can a bad actor make a probabilistic model do? Engineers in this space target prompt injection resistance. They test for complex, multi-turn jailbreaks, where a model is tricked into breaking its own safety guardrails through a carefully crafted sequence of conversational inputs. The second pillar is responsible AI, or RAI evaluation. This asks, who does the system systematically harm under normal operating conditions? Here, the focus is on measuring hallucination rates, how often the model confidently invents false information. Teams also analyze whether high-stakes decisions show disparate impact against protected classes. The third pillar is AI security. This asks, how can the deterministic, traditional software systems surrounding the AI model be exploited? This covers classic infrastructure vulnerabilities adapted for machine learning, such as API privilege escalation and data pipeline poisoning, where malicious data is intentionally fed into the system's retrieval mechanisms. This matrix maps the three pillars against their required toolsets. You have automated prompt fuzzers on one side, statistical bias analysis tools in the middle, and traditional penetration testing frameworks on the other. The engineering backgrounds required to operate these tools do not overlap. Assigning a single team to cover all three domains guarantees systemic failure. The strict distinction between these pillars becomes critical when we look at agentic AI. AI models are evolving from standalone chatbots into agents capable of perceiving context and executing autonomous actions in the real world. This schematic shows a typical agentic architecture. In the center, we have an internal enterprise AI agent. On the left, it draws data from a vector store, a database optimized for AI text retrieval. On the right, the agent has the authority to push actions to a Slack communication API. An adversary crafts a poisoned document containing hidden instructions and plants it inside the HR database. During a routine employee query, the agent unknowingly retrieves this document. The model reads the text and parses the malicious payload hidden within it. The compromised agent is hijacked by the instruction. It executes an unauthorized Slack message, leaking confidential employee demographic data to a public channel. When this breach occurs, which specific team owns the failure? The adversarial testing team must explain why the model prioritized the retrieved malicious instruction over its own foundational safety guardrails. The RAI evaluation team must analyze if the leaked confidential data disproportionately exposed protected employee characteristics, creating a specific legal liability. The AI security team must answer why the system architecture permitted an untrusted model output to execute an unverified API call. In an integrated agentic architecture, a single exploit triggers simultaneous, catastrophic failures across all three of these critical testing domains. Without explicit, predefined cross-functional coordination, this intersection, the convergence zone, is entirely indefensible. Moving from a technical exploit to practical compliance requires taking this three-pillar taxonomy and operationalizing existing industry frameworks. The adversarial testing and AI security pillars map directly to OWASP and MITRE Atlas, foundations for software security and AI adversary tactics. The RAI evaluation pillar maps precisely to the NIST AI risk management framework, targeting requirements for measuring fairness and safety. By organizing testing artifacts, like execution logs and remediation plans, against these specific framework subcategories, the organization instantly prepares itself for external audits. Mapping the technical testing process directly to standardized frameworks translates fragmented engineering work into a defensible, unified compliance strategy. For enterprise architects, the primary operational directive is clear. Define exactly which team owns which testing pillar during the architecture review, before a single line of code is deployed. High-risk and agentic deployments have a strict requirement. They must successfully pass all three independent evaluations prior to launch. Solving this governance crisis doesn't require rewriting the organizational chart or creating complex new reporting lines. It simply requires a shared vocabulary and rigid coordination protocols specifically for those moments when testing boundaries overlap. Implementing these protocols prevents ownership gaps from becoming active vulnerabilities as autonomous systems move into production workflows. A unified three-dimensional governance program provides the structural clarity required to manage the actual risks of enterprise AI.